Hi everyone. What this is going to be is essentially a brief overview of chapters 3 and 4, me giving like a very short synopsis of each section, like a mini lesson, if you will. So this is also kind of like if you had me for college algebra first semester, we made the big review sheet for the semester test, where we put an example down for every learning target. We're essentially going to do that here. So uh, as you follow along for this, I would have a piece of paper and you're going to need 8 sections. So 4 on front, 4 on back. You can either do it more horizontal or more in like quadrant style. It doesn't matter to me. I don't know if one's necessarily better than the other. What we're going to do is we're going to write the title for each skill, and then we're going to put an example or two, vocab, kind of the key overview. And I'm going to actually allow you what we make here to use on the test that we take. So it acts as a review, and it'll also act kind of as a safety net, a study guide that you can use while you actually take your chapter 3 and 4 test. So you get a piece of paper that looks like this. If you need to pause the video now, go ahead and do so till you're ready, but I'm going to start. So the very first section that we started with was chapter 3 in chapter 3, section 1. We looked at the fundamental counting principle and how we could use tree diagrams in order to count how many ways something could occur. So the fundamental counting principle says that if multiple events can occur in n1, n2, n3 ways, then all of the events can occur in n1 times n2 times n3 all the way down the line. So, example of this might be like how many different hamburgers can they make if there's 2 types of buns, 3 different types of toppings, and 3 different types of sauces. Well, it'd be 2 times 3 times 3, 18 different, items that they could make. So that's the fundamental counting principle. Fundamental counting principle is also why tree diagrams work. So tree diagrams allow us to count how many ways something could occur. So I'm going to ask you to make a tree diagram for each weekday being sunny or cloudy. So weekdays, well, how many weekdays are there? There are 5. So there'd be 5 branches of the first tree, and then each of the days could be sunny or cloudy. So each branch would have 2 more branches coming off of it. So the total would be like Monday sunny, Monday cloudy, Tuesday sunny, Tuesday cloudy, dot, 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 all the way out to Friday cloudy. How many different possibilities are there? There's 10. 5 for the first times 2 for the second. So that's a use of the fundamental counting principle. And that was section 3.1. Moving on. The next section, 3.2, we're going to do 2 sections for it. So the second box on your study guide, you could write at the top of it. Something I should have mentioned maybe before is it might be wise as you work just to title what each section is. So, oops, this would be 3.1, and then you can write what it was about. 3.2a, write what it was about, so that it'll help you keep things organized. 3.2a was on conditional probabilities. That's probabilities as you know an extra piece of information, and then we call that extra piece of information the condition. So conditional probability is the probability of an event occurring given that another event has already occurred, given that we know an extra piece of information. We write it mathematically as P for probability of B occurring, and then this right here means given that A has already occurred. So probability of B given that A has already occurred. And we're going to practice it. So a lot of times conditional probabilities occur with 2-way tables. So if you need to pause the video to copy down this table, go ahead and do so. But I'm going to assume that you've paused it and already done it. So the first question says, what's the probability that one person selected likes movies? So if I were writing this out, that's just the probability someone likes movies. Well, I can look and see there are 16 total people that like movies. How many in total were there? There are 50. So 16 divided by 50 is 32%, so 0.32. Second question, what's the probability the person is female given they like dance? Given they like dance means I know that we are in this column. This is my whole entire universe now. And I want to know what's the probability that they are female given that they like dance. So now I know my total is out of 18 because I know there's only 18 people that like dance. How many of them were female? 16. So 16 out of 18 would tell me the probability that someone is female given that they like dance. That turns out to be 89%. Last one. What's the probability the person likes sports given that they are male? Given that they are male tells me that my universe is now shrunken down into this row. I know that my universe has only 20 people in total. If I wrote it out, it'd be the probability that they like sports given that they are male. There were 20 males in total. How many of them preferred sports? 10. 10 out of 20 would be a 50% likelihood. And that is how we can calculate conditional probabilities. Most frequently that they occur in what we call two-way tables. Two-way tables because there's two things being categorized, preferred program and gender. 3.2 also had what we called independent and dependent events. Those were when two events occur and one may or may not have an effect on the other. So whether the fact that we knew something else occurred may or may not even matter. If the two events are dependent, then it's going to matter. The probability that A occurs first and then B occurs second is, well, equal to the probability of A occurring first times the probability of B occurring second, given that A has already occurred. If the two events are dependent, then I need to consider the fact that A has already occurred. If the two events are independent, then I just have the probability of A times the probability of B. B doesn't care that A has already occurred because the two events are independent. They are free from one another. So that's why it has a different formula. You'll also see, because we are calculating with and statements, we are going to be using multiplication. So in probability, if we are concerned with two events occurring in a certain order, and then it's going to be multiplication. So question number 1, it says, 8% of people have blue eyes. 3 unrelated people are selected. What is the probability each has blue eyes? So first we have to ask, is this a dependent or an independent event? This is going to be independent. The fact that one person has blue eyes should have no effect on whether somebody else has blue eyes if they're unrelated. So it would just be the probability of each having blue eyes. So what's that going to be? 8% for the first, and 8% for the second, and 8% for the third. So this is going to be pretty rare because only 8% of the population has it. And that turns out to be 0.0005 as a decimal. What's the likelihood the first has blue eyes and the last two don't? Well, the likelihood that the first one does is 8%, and the last two don't. Well, the opposite of 8% is 92%. So 0.92 times 0.92. So 0.08 times 0.92 times 0.92 turns out to be about almost 7%, 0.068. Question number 2. Same scenario as number 1, except it is 8 people out of 100 you sample have blue eyes. You select 3 of them, obviously without replacing them. They don't go back into the pool. What's the probability that each has blue eyes? You're going to see that this is actually a dependent scenario because the fact that we know something about the first one lets us know that the probabilities change for the second one because there's less people in the entire pool, because there's 100 people. If I have one less person, now it's only out of 99. So again, let's say I select 3 of them, obviously without replacing. What's the probability that each has blue eyes? Well, this would be 8 out of 100 for the first one. And now the second one needs blue eyes. Well, there's only 7 people that have blue eyes then out of there, and there's only 99 people left to choose from. And now there's only 6 people that have blue eyes out of 98 people left to choose from. You're going to see it's slightly different than the first scenario. So 8 out of 100 times 7 out of 99 times 6 out of 98, you get 0.0003. We'll do the other one again. What's the likelihood that the first does and the last 2 don't? Well, the first does is 8 out of 100 times the last 2 don't. Well, there's 92 people that don't, but now there's only 99 people to choose from because the first one was taken as blue eyes. And the last one doesn't. Now there's only 91 people that don't have blue eyes, and there's only 98 people to choose from. So I multiply those out. 92 over 99 times 91 over 98. And I'm getting 0.0690. So you can see in the second one, those are independent events because the probabilities of the second changed based on what happened in the first one. There's less people in there. So that's what an independent, or sorry, not a dependent event is when it changes. The first one is independent. So first one's independent, this one's definitely dependent. As you can see, the following probabilities were definitely dependent on what happened prior. 3.3 again considered itself with events, but it was whether two events could even occur at the same time. So mutually exclusive is when two events cannot occur at the same time. So two events are mutually exclusive if they have no overlap. So if I want to find the probability of A or B occurring, I can just add them together. Again, notice in this case, or means addition in probability. If they are not mutually exclusive, which means they do have some overlap, I need to subtract off their overlap amount because the probability of A or B is the probability of A plus the probability of B. But if they have some overlap, it got counted once in A and once in B, so I need to subtract it off once because it got double counted. So I would definitely write these formulas down. If you need to pause the video to do so, but I'm going to assume that you've already done it. So we're going to go back to that two-way table, and we're going to ask some questions about mutually exclusive or not mutually exclusive events. So question number one, what's the probability a person likes dance or movies? So it would look like this to start, probability of dance or movies. Well, I can look, what's the probability that somebody likes dance? Well, liking dance, there's 18 out of 50, or movies, 16 out of 50. Now I need to ask, was there any people that could have chosen dance and movies? Do they have any overlap? Well, if you actually draw these in, you're going to see that they have no overlap. Those are mutually exclusive events. There's nothing to subtract off. They have 0 to subtract off as their overlap. So the answer for that one would be just 34 out of 50, 68%. So there is the first one. The first one is for mutually exclusive events. Second scenario asks us, what about the probability a person is a man or likes sports? If I were writing this out, probability man or sports, probability that someone is a man, well, that is this row. You can see there's 20, so 20 out of 50 is the probability that someone's a man, or means addition, so add. What's the likelihood that they like sports? There are 16 out of 50, but the problem is this 10 right here got counted twice. It got counted once in the men group, once in the sports group, so I need to subtract it off because I've counted it twice. And then the total probability end up being 26 out of 50 or 52%. So if there's overlap, you need to subtract it off because it got counted twice. That's for not mutually exclusive events, items that do overlap. In 3.4, we started to look at the number of possibilities, whether order did or did not matter. So 3.4 was on combinations and permutations. There are formulas for them if you'd like to write those down, but I'm just going to rely on the calculator for this because it has the formulas built in. So we use combinations when order does not matter, and when you use permutations when order does matter. Because of order mattering and not mattering, you kind of might note that permutations for a specific scenario with the same numbers would always end up being larger than the combinations, because if order matters, then there's more unique ways to rearrange things. So that's why we have a different scenario, because if order matters, there's definitely more unique ways to rearrange items. So situation number one that we'll look at. Let's say I want to know the number of ways to pick 3 toppings for a pizza if they give me a list of 11, and they can say, okay, you're going to make a 3-topping pizza. How many different 3-topping pizzas can I make if there's 11 toppings to choose from? Well, the first question you should ask is, does order matter? If I said I want pepperoni, sausage, and peppers, and I called in, would that be any different than if I said I want sausage, peppers, and pepperoni? No, the order doesn't matter. So we're going to be working with a combination here. So I would type in the calculator. 11 choose 3 is how we would say that. This is how you would type it in. 11. And then if I go up to math, over to the probability option, I'm choosing option 3. 11 choose 3 is 1165. So there's 165 different 3-topping pizzas we can make if there are 11 toppings to choose from. Second scenario says, what if I'm concerned with the number of ways to select the first, second, and third batters out of an 11-player lineup? So it's actually the same type of question. How many ways can I pick 3 from a group of 11? But this time order matters, because if I said, Sally, Susie, and Callie, it would be different if I had said Callie, Sally, Susie, right? So order matters. That means we're going to be using a permutation. So I would do 11 permute. 3 is how we say that mathematically. You would type in the calculator 11 math over to probability, permute 3. And there's more numbers. There's more possibilities because order is important now. All of those ones where order wasn't important has more permutations now. So combinations, order does not matter. Permutations, order does matter. Next section, then we started chapter 4. The first thing that we started to look at in chapter 4 was on finding the expected value, which is another way of saying the mean, and then the standard deviation for a probability distribution. On the calculator sheet that I passed out in class, you can just follow the steps on the calculator sheet. It'll have it right there in section 4.1. Tells you how to find the mean and the standard deviation if you're given a probability distribution. So here's an example. Convert the following to a probability distribution, then find the mean, the standard deviation, and interpret. So they surveyed a number of employees, asked how many overtime hours that they worked. So essentially there were 6 people that worked 0 hours, 12 people that worked 1, 29 that worked 2 hours, ... Here's how we would do it. There were, 6 people that worked 0 overtime hours. Well, 6 people doesn't really tell me much if I don't know how many people, like how many employees there are. Well, if you add all this up, so you first have to add all this up to get the total. There's 192 employees in this business in total. So the probability that one of them worked 0 overtime hours is 6 divided by 192. What's the probability that they worked 1 overtime hour? Well, it'd be 12 out of 192. And then you just work your way down the list, dividing by 192. And that would be the probability distribution. It gives us a much kind of easier way to share the information. If I were sharing it with the boss and I said, oh yeah, 57 of your employees worked 3 hours of overtime, that's not as useful probably as saying 30% of the employees worked 3 hours of overtime. So it gives just the numbers in a way that might be a little bit more relatable in certain scenarios. So there's the probabilities. Now how do I calculate the expected value? You can do it by hand. You would multiply 0 times the probability of 0.03, 1 times 0.06, 2 times 1.5, 3 times 0.3, 4 times 0.22, 5 times 0.16, 6 times 0.08. You would get all those values and then you'd add them up. That will give you the expected value or the average. You can also just type it into the calculator as well. So this is what you would do. You follow the directions that are on the calculator sheet. It says go to Stat, Edit. In your list 1, you need to list all of the overtime hours. 0, 1, 2, 3, 4, 5, and I believe it was 6 was the maximum. Yep. And then you need to enter all of the probabilities. So the first one. So I go over to here, clear this list out by hitting clear enter, 0.03, all the way down, 0.06. I'll just do, just to show the next 2, 0.15. I think you get the idea. So you need to enter all of that in. Once it's, well, let's do it. 30%, 22%, so 0.3, 0.22, 0.16, 0.08. We should know it's valid because if I add all those up, it should be 100%. Sometimes it's off by 1% just due to rounding, but should add up theoretically to 100%. And then what I do next is I go to Stat, over to Calculate, and it's option 1 variable statistics, or one variable in this case is overtime hours. I need to tell it where I put the list. List is in L1. I need to tell it where the probabilities are, the frequencies. That's in L2. If there's nothing in there, you need to tell it L2. This is where you get to. L2 is this blue key right here. So you hit second. Looks like you're hitting 2, but it's really list 2. And then you run Calculate. There's your average, 3.42. And then the standard deviation in this case is right there. 1.43, 1.44. There you go. So what that means then, the interpretation is that so if I use the empirical rule, going back to the prior chapter, we know bell curve. Empirical rule tells us here's our average, 3.42. If I go up by 1.44 and down by 1.44, my upper end would be 4.86. My lower end would be 1.98. That's one standard deviation. And we know by the empirical rule that 68% of measurements are within one standard deviation of the mean. So we would know the majority, about 68% of workers, work between 1.98 and 4.86 hours of overtime. That's where probability distributions start to get applied. So that's 4.1. You should be able to do a problem like that. 4.2, and then 4.3, the last two sections, dealt with specific types of probabilities and their distributions. So the first one was a binomial distribution. We use binomial distributions when we are given a percent of success for each trial. That percent of success needs to stay the same. These need to be independent trials. And we want to know what's the likelihood of getting X successes out of a set number N trials. You can use the formula, or you can use the built-in program in the calculator for it. Be aware PDF is when we want a particular case, and then we use CDF when we have situations we want to combine ones, that or less. And then also be aware for binomial distributions that the average value is always n times p, and the standard deviation formula is the square root of n times p times q. We use that when we want to get ranges for like the empirical rule, like we just did a second ago. We want to know where the middle 68% are. So if you need to, definitely probably jot this down and be aware that you're going to be using binom either PDF or CDF. So here we go. Questions. The quarterback has a completion percentage of 62%. If he makes 10 throws, what is? So why is this a binomial? Because we have a set number for the probability. 62% of it is our success rate. We have a set number of trials, 10, and we want to know the likelihood of him getting a certain amount of those 10 as a success. What's the likelihood that he gets exactly 8 completions? Well, 10 trials for n. Probability of success is 62%. So if I use the calculator, binom PDF 10.628, where do you get that? It's under the distribution menu, second distribution. You can scroll down or you wrap back around. It's option A. And then you input the values for n, p, and x. You get 14% likelihood that he'll have 8 completions. What's the probability he'll have 6 or more completions? 6 or more would mean 6, 7, or 8. So there's two ways I could do this. I could do binom PDF for 6, binom PDF for 7, binom PDF for 8, and add up all 3 of those. Or instead of doing that, I'm going to be more clever. I'm going to find the opposite of 6 or more. The opposite of 6 or more is 5 or less. And then I can just do binom CDF once instead of doing binom PDF 3 times and get the value. So what's the likelihood he has 5 or less completions? Well, that turns out to be about 32%, which means he's going to have 6 or more completions 68% of the time out of his 10 throws. So CDF is used if I want a set value or less. So 5 or less is the opposite of 6 or more. Last question is, what's the mean, what's the standard deviation, and what is the interpretation? Well, if he does 10 throws and he gets 62% of those usually as a completion, we would expect out of 10 throws, he's going to get on average about 6.2 completions. If I use the standard deviation formula of the square root of n times p times q, I see that the standard deviation is about 1.5. So he's usually no more than 1.5 completions away from his average of 6, which means the majority of games in which he attempts 10 passes, or maybe his first 10 passes, he completes between 4.67, which is 1.53 below 6.2, and 7.73, which is 6.2 plus 1.53 of his first 10 passes. It gives us a range of values for which the majority of the time he's in between those number of completions. And that was the second to last section. That's for binomial. The last section dealt with the last 2 types of distributions. The first one is called a geometric distribution. It is used when we have a probability of success but this time we want to know what's the likelihood that we have to go a set number of trials before we get our very first success. So Geometric's dead giveaway is they're always asking you what's the likelihood that the first success occurs on this trial. So if they're using the phrase first success, it's a dead giveaway, it's a geometric. The very last type of distribution is called a Poisson distribution. It's named after a French mathematician whose last name was Poisson, who discovered the formula for this. We use it when we are given an average value and we want to know the likelihood of getting something different from that average over a period of time, area, or volume. There's a formula for it. I would recommend, though, just to use the built-in program in the calculator. It's Poisson PDF. The first thing it asks you for is the average, and the second value asks you for the value that you want that's going to be different from that average. Example, a car salesman is successful on 5% of his attempts. What's the likelihood that his first successful attempt for a day occurs on his sixth client? This is a geometric because they're saying his first successful attempt, so dead giveaway, it's geometric. So I would do PDF, 5% success rate. What's the likelihood I have to go 6 trials in order to get my first success? The likelihood that that occurs is about 4%. So geometric PDF. Last scenario. The CDC allows for an average of 5 parts per billion of lead in a glass of drinking water. What's the likelihood that a glass of water contains 10 parts per billion? So this is a Poisson because they give me an average and ask you something different from that average. So what's the likelihood it's actually 10 if the average is typically 5? So Poisson PDF, first value you give is the average, second value you give is the number different from that average. The likelihood of it being 10 parts per billion is about an 18% likelihood if it's on average 5 parts per billion. And that's chapters 3 and 4. I hope this helps. And if you have questions, always feel free to reach out to me. Thank you very much.